Good evening, afternoon, or whenever you happen to be watching this, ladies and gentlemen. We're going on to 3.3 day 2 of the derivative. Okay, now we're going to be finding first and second derivatives of functions and solving problems using derivatives. Alright, well, second derivative, as it says right there, is simply the derivative of the derivative. So basically you do it once, then you do it twice, and you got your second derivative. Okay, now notation-wise, basically, if you're using an apostrophe, you just use two of them. Or if you're using this dy dx sort of notation, you do d squared y over dx squared. I know it seems a little bit confusing, but that's the way it works, mostly because of this notation right here. So you still have the original function, and the other two just says that you're doing the second derivative. Alright, that being said, if I want the second derivative of a function such as this, a polynomial function, well, first thing first, I need the first derivative. So my first derivative is going to be 8x to the third minus 6x to the first plus 13. Alright, so now I've got that, but that's not good enough. I need the second derivative. So y double prime equals 24 x squared minus 6, and the 13 goes away. So there's my second derivative. Alright, I'd like to do another example here just to demonstrate what you can do for a situation like this that is a little bit messy as is. Alright, so if I want the second derivative, first thing is this is kind of a messy function, so I'm going to clean it up. So again, f of x, again, notice no apostrophe, so I'm not doing a derivative yet. Okay, instead of having this fraction like this with the x up on top, in a situation like this, I think it's nicer to think of the 5/6 as a coefficient, and then bring the x to the whatever power, in this case -2 out in front, and it's a little nicer to start doing our derivative stuff. Alright, likewise here I have minus, again that's technically a 1 up there, so this is minus 1/2, and then again pull the x to the front, x to the negative first, and I think this format is just a little nicer to deal with. Okay, depending on how you handle things, you may or may not want to do that, but there's an option for you, just in case. Okay, moving on now, here's my first derivative. Okay, when the -2 comes out in front, the -2 comes out and cancels with the 6 down to a 3, although the negative sign lives to tell the tale, so it's -5. That's a 5 right there, believe it or not. And then it's a 3 on the bottom now. That's the worst 5 ever. Okay, and then again, remember, x, we're reducing by 1, so this gets me down to the -3rd. Alright, so again, I've got my minus sign right here, but the -1 comes out in front, hitting the minus sign, making it a plus. But of course, 1 times 1/2 is still a 1/2, but then the x again drops down to a -2. Okay, but that was just the first derivative, so let's get to the second derivative. So now f double prime of x. Okay, now what's convenient here is the -3 comes out in front and cancels with this 3, and the negative cancels with this negative, so actually this just becomes a nice clean 5. And then becomes x dropping by 1, gives me x to the -4th. And now the -2 comes out in front, okay, canceling the 2, but the negative sign makes it through, so this is now a minus 1, if you will, x to the -3rd. And there's your function as is. Or I guess your second derivative, but you know what I mean. Alright, so let's move on to some application word problem kind of things based on derivatives. Okay, now we may or may not need the second derivative, it just all depends on what's being asked, so make sure you pay attention to the question. Alright, so this one says, what's the equation line perpendicular to that particular function at the point 3,8? Well, as soon as I start talking perpendiculars, I'm starting to talk about slope, and as soon as I'm talking about slope relative to derivatives, that's the first derivative. Alright, so basically what I need now for this guy, remember, is he's going to be some, barrel of monkeys monkey graph looking thing. So his slope is constantly changing, so that's why I need to specify a particular point. And to find the exact slope at that point, first thing I need is our derivative. So call it y prime, 3x squared minus 4. Okay, now again, this represents the slope at any point along the curve, and I want the point 3,8. Specifically, I care about the 3. So basically at this point, I'm going to plug in x equals 3 into the derivative to find out what the slope at that particular point is. So now my slope is what I get by plugging in here. So that's going to be 3 times 3 squared minus 4, and a little button pushing or mental math later, 9 times 3 is 27, minus 4 is 23. Alright, so there's the slope of the curve, but I want to be perpendicular to that. So the slope of any perpendicular is, of course, the opposite reciprocal. So now this becomes -1/23rd, which admittedly is not the prettiest number you've ever seen, but there it is. Okay, that being said, now I want the equation. So in my equation, I can go to point slope form because I do have a point and I do have my slope. So now I'm talking y minus 8 equals icky fraction x minus 3, and we'll just kind of clean this guy up until the y is by itself. So a negative 1/23 x plus 3/23. Yuck. And of course we'll just add 8 to both sides here. Okay, now I kind of show the work here because I am about to cheat a little bit, if you don't mind. So this is negative 1/23 x, and the easiest way to add 8 and 3/23 is to turn it into a mixed number. So like I said, I'm just going to cheat and call this 8 and 3/23. Alright, of course you can multiply the bottom times the front number and add it to the top if you want the improper fraction of it, but in this case I'm going to be lazy and stop right there. Alright, let's take a look at another problem. It's similar but not completely the same. I'm going to find the equation of the line tangent to this function at that point. Alright, so again, if I'm talking about tangent, I'm talking about basically the slope of a line that touches this curve exactly once at this point. So here we go. We need, again, slope, so that means we need a derivative. So my derivative for this guy, okay, the bad news is this is going to require the quotient rule. Alright, so here we go. Quotient rule again says I want to take the denominator times the derivative with respect to x of my numerator minus my numerator times the derivative with respect to x of my denominator. Pardon me for being a little sloppy right there. And that's all over my denominator squared. Alright, and then again we just got to clean that guy up. Okay, now the good news is, well, let me not get too ahead of myself. Okay, the derivative of 12 is actually just 0. So the good news is the left half of this thing just goes away. So, bye-bye. Alright, now I got my minus sign, and then derivative, well, derivative of x squared plus 5 is 2x. So actually in just a second my whole numerator is going to clean itself up fairly nicely. And I've still got my x squared plus 5 squared. And so my final derivative, which again remember is going to be what my slope is going to be a negative 24x on top of, again, the thing that you may or may not want to FOIL out depending on your personal opinion. Okay, but there's my slope. Again, I would want that at the point negative 1, 2, but again, all I really care about as far as plugging in purposes is that negative 1. So basically at x equals negative 1, my slope is negative 24 times negative 1 over negative 1 squared plus 5 quantity squared. So it looks kind of messy right now, but it unfortunately does clean up a little bit nicely. So that's 24 over, pardon me for doing this quickly, but this is 1 plus 5, which is 6, squared is 36, and that actually reduces quite nicely by 12 down to 2/3. Okay, so now again I've got a slope, I've got a point, so now kind of second half of my work here, I've got y minus 2 equals at 2/3 x minus negative 1, so I'm just going to write plus 1, and then you just clean it up until the y is by itself, and you're in business. So that's plus 2/3. Again, adding 2 to both sides right here, I've got a situation where I can go with a mixed number without causing too much issue. So 2/3 x plus, again, if you prefer, you could call this 6/3 and make it an 8/3, although I would certainly accept 2 and 2/3 at that point, but whatever works for you. But there it is. Alrighty, nice little word problem-y sort of thing here, sort of. Alright, so from physics is a wonderful thing for calculus connections, but here we go. Okay, we know that the time it takes for a pendulum to swing is 2 pi times the square root of the length of the pendulum divided by gravity. Okay, so that's g for gravity, and here we go. So if I want to find dt over dl, okay, now one thing we need to be able to do is pay attention to what these letters mean. Okay, the t basically is the t from right here, so that's basically your original formula, if you will. Okay, and then the L down here is basically the variable that's in the formula, because there's a lot of things that don't look like numbers in here, but there's actually only one of them that is actually a variable, which is the L. Of course, pi is pi, and then g is a constant, because we know the acceleration due to gravity, depending on if you're talking about English or metric units, is a constant. So there's basically what's going on here. This is the variable for your function. In this case, our function is t. And then this is the variable inside the function, if you will. Okay, if that helps, great. But whatever the case, I'm trying to find dt dl. Alright, so again, basically what we're doing is thinking of all these things as constants except for the L. So admittedly, one thing you might do, although I don't know if it's required or not, but you kind of break this thing into the appropriate pieces. So I could take my 2 pi and leave that on top of, again, the g is a constant, so I can take the square root of g and put it all right there. And then another thing that might be nice to do, because we're about to do a derivative, is instead of leaving this as a square root of L, write this as L to the 1/2 power. Alright, if you do this, it's probably a little easier to see what's about to happen. Okay, which is, again, L is my variable. I've got the exponent on it, so I bring the 1/2 out in front. And I am going to show a little bit of work here just to hopefully clarify things. And that's going to be times the 2 pi over root g that we had. And then that's going to be times this L, which again, I need to reduce that exponent by 1, so the positive 1/2 becomes a negative 1/2 now. Okay, and let me just take one more step to clean this guy up a little bit. So dt dl is now, okay, good news is the 2 and the 2 cancel each other out. So this is simply pi over root g. And then you kind of have options here. We could leave it as L to the negative 1/2, or if you wanted to, you could bring the square root of L down to the bottom, whatever works for you. But I'm going to bring it to the bottom just because I feel like it. So this is the square root, because kind of we got this g and I've got the L, so now I can kind of smash them down underneath that altogether, and that to me just kind of looks nice. No, I would not expect you to rationalize the denominator in this sort of case. I would be very happy with that sort of an answer, or kind of like what I said, if you wanted to leave it more like pi over root g, you could do that and then leave the L to the negative 1/2 as kind of its own little guy out in front. Either one's good for me as long as it's good for you. Let's go with another example from physics here, because as we know, physics is fun. Alright, okay, so here's the formula for the height of a projectile. Height equals 1/2 acceleration due to gravity times time squared plus the initial velocity vertically, if you will, times time plus the initial height. Okay, so initial velocity is going to be some kind of a constant, because that's how fast the thing's being either thrown or shot or whatever the heck we're talking about. And the initial position, again, that's just how high you are when you're starting. Alright, so here's this. So we want dh over dt again. My function is h, again there's just the h, so that's all we're talking about there, and then the t is just the variable in there. So the t is a variable, every other letter you see is actually going to be replaced by a number. Remember, acceleration due to gravity is going to be a constant as well. So dh dt is going to be, the 2 comes in front, cancels very nicely the 1/2, and leaves us with a times t to the first, so at, because that's where it's at. And then this t right here, first power, brings a 1 in front. The t to the first becomes t to the 0, so effectively disappears, and that just leaves me with v sub I. Okay, again, this is a constant. Derivative of any constant is 0. So there is my derivative dh dt. Okay, now if you're taking physics, hopefully that looks familiar from something else, and kind of a dead giveaway here, but hey, that's the formula for, what do you get when you take velocity plus acceleration times time? Well, that's your kind of final velocity. Okay, now what we get if we take the derivative with respect to time. So basically, if we wanted to, before I do that, I could write this formula as velocity equals initial velocity plus acceleration times time. That's probably more like what you've seen before. So if I want that, I want to take dv over dt, and that derivative, okay, the v sub I is going to go away, and then the at just becomes a. So the derivative of velocity is acceleration. Kind of nice how the height versus velocity versus acceleration, kind of one leads right into another one through derivatives. I think that's pretty cool. Alright, just in case you didn't get the hint from what I said in the last slide, is, some formulas are derived by taking the derivative of other formulas, and I just think that's totally super cool. For example, let's take another one. For a circle, area equals pi r squared. Well, what's a prime? Alright, well, there's a prime, so the derivative of area, well, taking the derivative of this should be pretty quick. Again, pi is of course a constant, so I just bring the 2 out in front, multiply it by pi, and get 2 pi, and then my r squared drops by 1, becomes an r. Well, hopefully, very, very quickly, you recognize that as circumference. Alright, So basically A prime is circumference. So nice little connection between circles. There's a lot of formulas where one, take the derivative, you get another one of things that are kind of related one way or another to an object. I don't know, I just think that's super cool, and it's really where calculus is awesome, and that some of these mathematical things all kind of start getting connected to each other and eventually start making a whole lot of sense in the context of everything that happens. But oh well, I think it's cool. Hopefully you thought it was at least a little bit cool. So there it is. Alright, so not much more else to say other than there's your assignment. Okay, so 1 through 9 odds. Okay, now you did 1 through 10 all previously, and just take the odd ones now. I think by just doing the second derivative of those, you kind of got half the problem done already. Pick it up and do the 27 to 35 after that. And of course, as always, if you have any questions, make sure you ask me in class. I'll see you then.